Welcome to this course, which introduces the concept of using vector databases in Retrieval-Augmented Generation, or RAG, applications. By enrolling in this course, you'll improve your data retrieval skills, gain valuable expertise in similarity search and vector databases, understand how they differ from traditional databases, and recognize their importance in recommendation systems and Retrieval-Augmented Generation, or RAG, applications. You will build on this foundation with practical experience using ChromaDB, one of the leading vector database solutions. You'll apply what you've learned by creating a real-world recommendation system powered by ChromaDB and an embedding model from Hugging Face. This project will enhance your understanding of how vector databases improve search and retrieval in AI-driven applications. Throughout the course, you'll engage in practical exercises to refine your skills in database management, similarity search techniques, and advanced vector operations. By the end, you'll have a thorough understanding of vector databases and similarity searches, which are essential components of the RAG pipeline. This course is designed for learners who want to build practical knowledge and experience with vector databases and similarity search, particularly in the context of RAG. This course would be ideal for software developers, engineers, current or aspiring data scientists, and AI engineers, AI enthusiasts, professionals transitioning into AI or data science roles, and computer science students. This course only requires prior knowledge of Python. Other useful knowledge includes a basic understanding of generative AI and foundational software design principles. This course has 2 modules. We encourage you to set aside time to complete all the modules. The first module is Introduction to Vector Databases in ChromaDB. In this module, you will be introduced to the concept of vector databases, and you will learn how vector databases serve as the foundation of recommendation systems and how they differ from traditional databases in storing and managing vector data. This module examines different types of vector databases and their applications, particularly focusing on ChromaDB. You will explore the ChromaDB architecture and learn about common coding practices for its operations. You will gain hands-on experience performing basic vector database operations. You will also learn about similarity search and get hands-on experience performing similarity searches both manually and with ChromaDB. By the end of this module, you will have a clear understanding of the transformative role of vector databases in modern data management systems. The second module is Vector Databases for Recommendation Systems and RAG. This module helps you understand the connections between vector databases, similarity search, recommendation systems, and RAG. It covers how to perform essential database operations using ChromaDB. You will gain a deeper understanding of both recommendation systems and ChromaDB with hands-on experience analyzing employee data and building a food search recommendation system. By the end of this module, you will have a clear understanding of the critical role vector databases and similarity searches play within RAG applications. To get the most benefit from this course, watch all the videos and review the readings. Then reinforce your learning by completing all the hands-on activities, such as the labs and the practice and graded quizzes. We encourage you to participate in the course discussion forums to connect with others taking the course or to get help from the course staff. So there's a lot to cover here. We are thrilled that you will join us on this learning journey. Let's get started. Good luck! Welcome to this overview of the Professional Certificate in RAG and Agentic AI. AI is evolving beyond traditional models, enabling smarter applications. Retrieval-Augmented Generation, or RAG, enhances AI's ability to provide accurate, context-aware responses by integrating real-time information retrieval. Multimodal AI is another advancement that allows systems to process and integrate various types of data, text, images, audio, and video, enabling more dynamic and interactive user experiences. Agentic AI represents a further shift, equipping systems with the ability to reason, plan, and autonomously execute tasks. While each of these approaches can work independently, they can also be combined to create more powerful and adaptable AI systems. Through this program, you'll gain the expertise to build and implement AI applications that combine these powerful techniques, preparing you for the next wave of AI-driven innovation. Whether you're looking to advance in software engineering, machine learning, or data science, mastering RAG, multimodal, and agentic AI will give you a competitive edge in the evolving job market. This RAG and agentic AI program consists of several short courses that cover generative AI applications, RAG applications, vector databases for RAG, advanced RAG with vector databases and retrievers, multimodal generative AI applications, AI agents, agentic AI fundamentals with LangChain and LangGraph, and finally, agentic AI with LangGraph, CrewAI, AG2, formerly AutoGen, and BAI framework. Each topic corresponds to an online course that you can complete independently. Each course consists of 2 to 3 modules. Completing courses covering different topics and the required projects will earn you the completion certificate. Let's look at the contents of each course. Your journey in the first course begins with the basics of generative AI, along with an in-depth look at prompt engineering, in-context learning, and prompt templates. You'll also be introduced to the LangChain framework to build generative AI applications, which streamlines AI workflows by enabling more structured and efficient prompt chaining. In the second course, you'll be introduced to the key components of Retrieval-Augmented Generation, or RAG. You'll also learn how to implement RAG using LangChain. This course also introduces you to Gradio, helping you set up an interface to interact with AI models. Finally, you'll work with Llama Index as an alternative to LangChain, gaining hands-on experience building a bot with Llama Index and IBM's Granite model. The third course introduces you to the transformative role of vector databases in modern data management systems. You will gain insights into ChromaDB's architecture, common coding practices for its operations, and hands-on skills in performing basic vector operations. Similarity search is also explained with hands-on labs. Finally, you will build a recommendation system using a vector database and an embedding model. The next course provides a deep dive into advanced retrievers and retrieval patterns, equipping you with the skills to implement and optimize retrieval strategies within a RAG system. You will work with FACE, a powerful vector database used for efficient similarity search. You will also build a RAG application using FACE, LangChain, and Gradio. The fifth course begins with an in-depth introduction to multimodal AI, focusing on how AI systems process and integrate multiple data types. You will evaluate speech recognition and text-to-speech technologies, along with computer vision. You will work with tools such as OpenAI Whisper and Mistral to develop multimodal applications. You'll also explore how models like DALL-E generate images and the fundamentals of image captioning. Finally, you will dive into multimodal retrieval and search and multimodal question answering and chatbots, learning how cross-modal retrieval techniques enhance search engines and recommendation systems. The sixth course provides a detailed foundation for building AI agents. It covers function calling, chaining, and tool orchestration to enable AI systems to interact with external tools and execute tasks effectively. You'll also learn how to manually handle tool calls by parsing the outputs of language models. Finally, you will leverage LangChain's built-in agents, including DataFrame and SQL agents, to analyze structured data, generate visualizations, and perform database queries through natural language. The seventh course helps you use LangGraph and LangChain to develop stateful workflows. You'll explore key architectures such as agents and React agents, applying them to real-world applications. Additionally, the course introduces multi-agent system design and agentic RAG architecture, equipping you with skills to build scalable, robust applications. The eighth and final course helps you design AI workflows using state-of-the-art design patterns and multi-agent orchestration frameworks. You will be introduced to agentic frameworks such as CrewAI and LangGraph. Finally, you will dive into alternative agentic frameworks, IBM's BAI framework, and AG2 to implement multi-agent collaboration and conversation-driven systems. This program presents you with practice and graded quizzes to evaluate your learning. The graded quizzes carry a weightage that contributes to the course completion. These courses have hands-on labs and projects that contribute to the course and program completion requirements. Finally, after you have successfully completed all of the courses, you will be awarded the completion certificate for this IBM program, a credential valued by many employers. We wish you the very best and hope you enjoy this journey.
Welcome to this video, where you will explore essential vector database concepts. Traditional databases have been the standard for data management. With the availability of increasingly complex data types, the need for a more advanced solution has led to the development of vector databases. After watching this video, you will be able to discuss the importance of vector databases, describe vector database characteristics, and explain vectors and their elements. Companies use vector databases as libraries to find information, mine data, and teach computers how to learn. Vector databases simplify data storage, organization, and retrieval by organizing data points in a multidimensional space based on their proximity. You can retrieve vector data representations from their databases to perform analytical tasks, such as grouping items, classifying items, and suggesting relationships among items. Let's take a closer look at these uses. Vector databases handle complex data types and the analysis of non-traditional data, including relationship data such as social likes, geospatial data, and genomic data, which are difficult for traditional systems to store and manage. When using traditional databases, these data types often need a lot of pre-processing and transformation. Vector databases are great at handling complex data types for easy storage, fast retrieval, and complex data analysis. Vector databases can quickly and accurately locate related items, known as a similarity search, based on each database item's proximity to each other in the high-dimensional space where the vectors represent data. Similarity searches are essential for finding images and sounds, receiving and providing suggestions or recommendations, and genetic analysis. Vector databases use techniques including distributed computing, indexing, and parallel processing to quickly manage big data sets and process queries. Whether your domain is biology, healthcare, e-commerce, social media, or traffic planning, your industry depends on the ability to store and analyze enormous amounts of data quickly. Vector databases can help with climate analysis, calculating patient outcomes, delivering product recommendations, sharing social connection suggestions, and conducting traffic analysis. Vector databases are an integral component of machine learning and artificial intelligence (AI) systems. They are a natural way to store and explore machine learning data. Vector databases easily integrate into machine learning pipelines and speed up the creation and release of AI-powered apps. Traditional relational databases store information in the form of tables. At its core, a vector database stores data as high-dimensional vector data, also referred to as vectors. Vectors are mathematical objects that are defined by their size and direction. Vectors can represent many kinds of data, including images, sounds, text files, pattern data, map data, genomic information, and others. A vector in a vector database is a mathematical way to show data points in a place with more than one dimension. A vector, an array of numerical values that relate to different features or attributes of the data, is used to show each data point. Each numerical point is a dimension. For example, suppose you are looking for books on an online platform. The platform contains multiple books or novels based on fiction, nonfiction, and science fiction. Now, see how you can represent these books in terms of vectors. For example, a fiction book uses vector numbers of 1, 350, 2003, and 4.5. A nonfiction book uses vector numbers such as 2, 250, 2015, and 4.8. And a science fiction book uses vector numbers of 3, 400, 1990, and 4.2. Here, the first number represents the genre. For example, the number 1 is for fiction, the number 2 is for nonfiction, and the number 3 is for science fiction. The second number represents the number of pages in the book. The third number represents the book's publication year, and the fourth number represents the book's average rating. Next, let's say you are interested in science fiction books with approximately 200 pages and ratings between 4.7 and 5.0. Next, review the list of science fiction books available online. Book 1 contains vector values of 1, 180, 2010, 4.6. Book 2 contains vector values of 1, 220, 2005, 4.8. Book 3 contains vector values of 1, 210, 2015, 4.9. Book 4 contains vector values of 1, 190, 2018, 4.7. And Book 5 contains vector values of 1, 200, 2012, 4.5. Rather than searching the entire platform, these vector points provide a better experience and help you locate science fiction books with approximately 200 pages, with a rating between 4.7 and 5.0. In this video, you learn that vector databases simplify data storage, organization, and retrieval of complex data types, including images, likes, sounds, text files, pattern data, map data, genomic information, and others. You can use vector databases for analysis tasks that group items, classify items, and suggest relationships among items. Vector databases, an integral part of machine learning and for data in diverse domains, offer high performance and scalability. Vector databases store data as mathematical objects defined by size and direction. Vector databases use distributed computing, indexing, and parallel processing techniques to quickly manage big data sets and process queries. And a vector is an array of numerical values relating to different features or data attributes. Welcome to a video about types of vector databases. After watching this video, you will be able to categorize popular vector databases based on their types, capabilities, and vendors. Contrast the functions and characteristics of dedicated vector databases with databases that support vector search. And identify popular vendors of dedicated vector databases and databases that support vector search. As the name suggests, in-memory vector databases store vectors directly in memory. This approach enables swift read and write operations, making these databases ideal for applications that require rapid access to data, including real-time analytics and recommendation systems. In-memory database vector databases include Redis AI and TorchServe. For example, Redis AI is an in-memory vector database that supports storing and querying vectors for tasks like similarity search, classification, and clustering. Next, disk-based vector databases store vectors on a disk. This method suits large datasets that exceed memory capacity. These databases employ sophisticated indexing and compression techniques to enhance storage and retrieval efficiency. Disk-based vector databases include Annoy, Milvus, and Scan. As an example, Annoy, which stands for Approximate Nearest Neighbors Oh Yeah, is one database in this category. Annoy stores vectors on disk and constructs indexes for quick retrieval applications. Annoy reports that it's built for fast approximate nearest neighbor searches and is ready for recommendation systems and information retrieval applications. Distributed vector databases spread vector data across multiple nodes or servers. Distributed vector databases provide horizontal scalability and fault tolerance, making these databases suitable for managing massive datasets and high-throughput tasks. Distributed database vendors include FICE, Elasticsearch with Vector Plugin, and DaskML. One notable example is Facebook AI Similarity Search, or FICE, which is a distributed and optimized database designed for similarity searches in high-dimensional spaces and partitioning data across nodes to achieve scalable and speedy searches. Graph-based vector databases model data as graphs, with nodes and edges representing vector attributes or embeddings. These databases excel in capturing complex relationships and facilitating graph analytics. Graph-based vector database vendors include Neo4j, Amazon Neptune, and TigerGraph. For example, Neo4j is a graph-based database that supports storing vectors as node properties or attributes. Neo4j allows queries and vector data analysis within the context of a graph. Neo4j capabilities support social network analysis, recommendation systems, and knowledge graphs. Next, let's learn about time series vector databases. Time series vector databases manage data collected over time intervals and represent this data as vectors. These databases serve as robust tools for analyzing temporal patterns and anomalies. Some notable databases in this category include InfluxDB, TimescaleDB, and Prometheus. InfluxDB, a vendor in this space, allows vector storage alongside time-stamped data. This capability enables querying and analyzing time series vectors to detect patterns, forecast trends, and monitor system metrics in IoT, monitoring, and anomaly detection applications. Next, let's contrast dedicated vector databases with databases that support vector search. They are different from each other. Let's learn more. As the name suggests, dedicated vector databases are systems that use their own special characteristics and optimizations to store, index, query, and analyze large amounts of vector data quickly and accurately. Similarity search, clustering, and classification work more efficiently using vector databases. Next, discover the essential characteristics of dedicated vector databases. First, to store and retrieve vectors quickly, dedicated vector databases often use unique data structures like reversed indexes, product quantization, and locality-sensitive hashings, or LSH. These databases support vector operations like nearest neighbor search, similarity search, and distance calculations, which lets users do complex searches on vector data. Dedicated vector databases are made to be scalable so that users can store and query big vector datasets quickly across clusters or distributed systems. These databases put speed first, using optimized algorithms and data structures to get quick answers to queries, even for vector data with a lot of dimensions. And users can change the parameters for indexing and searching to get the best results for certain use cases or types of data. Some currently popular dedicated vector databases include FAIS, Facebook AI Similarity Search, Annoy, Approximate Nearest Neighbors Oh Yeah, and Milvis. Next, in contrast, let's examine how other database technologies support vector search. Databases that support vector search are either regular database systems or data processing frameworks that let you store and query vector data. Even though these databases may not be made for vector operations, they have tools or add-ons that let users perform vector searches along with other types of queries. So, what characteristics are important for these databases? These databases let users store vector data as part of their data model. This data can be stored as blobs, arrays, or user-defined types, or UDTs. Some databases let you organize vector data using standard or custom index structures. This makes it easy to get vectors based on metrics like similarity or distance. Many databases have add-ons or integrations that let users take action on vector data using special libraries or plugins. For example, when performing similarity searches or other vector-related tasks, users can use external tools. Though these databases allow vector search, they might not be as fast or as well optimized as dedicated vector databases. Users must consider functionality, performance, and scalability relevant to their needs. Here are some database vendors that support vector search. First, Single Store with Vector Database Processing works with IBM WatsonX.ai. Next, Elasticsearch has its vector add-on. PostgreSQL includes its PostGIS add-on for vectors in space. MySQL has its own indexes for vector search. Redis AI performs vector functions in memory. And Apache MongoDB and Apache Cassandra support vector searching with flexible schemas. In this video, you learn that vector-based database types include in-memory, disk-based, distributed, graph-based, and time-based databases. Vector-based databases speed performance for recommendation systems, social network analysis, knowledge graphs, graph analysis, and other complex tasks. Dedicated vector databases use data structures, reversed indexes, product quantization, and locality-sensitive hashing (LSH) that provide scalability, deliver speed, and enhance customization. Popular database vector database vendors include FAIS, Annoy, and Milvis. Databases that support vector search are either regular database systems or data processing frameworks that let you store data as blobs, arrays, or user-defined types. And notable vendors that support vector search include SingleStore with its support for IBM WatsonX.ai, Elasticsearch, PostgreSQL, MySQL, Redis AI, Apache MongoDB, and Apache Cassandra. Welcome to this video, where you can explore how companies and individuals use vector databases. After watching this video, you will be able to describe how you can use vector databases to analyze images and video, explain how vector databases enable recommendations, describe vector databases that support geospatial analysis and location-based services, and summarize how vector databases deliver social and marketing insights. You can use vector databases to perform feature extraction and representation, similarity searches, and process real-time data. Vector databases store high-dimensional feature vectors to perform feature extraction and representation. You can then view aspects of images, such as color histograms, texture descriptions, or deep learning embeddings. Similarity searches use a vector database's ability to store feature vectors. You can employ these capabilities to locate images, summarize videos, and suggest images and videos based on content. Real-time access vector databases provide horizontal scalability for real-time data storage. You can use these capabilities to perform video surveillance, object recognition, and live event analysis. For example, a photo-sharing app stores embeddings or small versions of user photos in a vector library. When you add a new image, the app looks at the embedding to see if it matches the other photos in the database. If the photo resembles other photos, the recommendation system suggests other similar photos that can be used to tag or organize albums. Next, let's explore some applications of system recommendations. Embedded storage and nearest neighbor search incorporate numerical representations of items or entities, known as embeddings, generated by the recommendation system. You can access the vector data's likes and traits to provide improved personalized suggestions. To deliver performance improvement and scalability, vector databases provide scalability to handle additional searches and vectors that improve query processing and indexing. These capabilities power fast, scalable recommendation services for large numbers of concurrent users. Vector databases provide cross-domain suggestions using embeddings, enhancing recommendation systems' completeness. For example, a streaming service keeps movie embeddings in a vector library. After you watch a movie, the system uses embeddings of related movies from the database to recommend other movies you might like. To store and index data efficiently, vector databases use indexing methods like rtree or quadtree to store geospatial data like addresses, polygons, GPS locations, and more. These capabilities provide answers for spatial queries, like closeness searches, range queries, and spatial joins for GPS information and other mapping needs. Another task is the provision of location-based suggestions. Vector databases combine geospatial data with user preferences and location information to suggest nearby events, services, and places of interest. Vector databases specialize in delivering real-time geospatial analytics. Vector databases can process real-time streaming data, group items together spatially, and recognize spatial patterns. These capabilities power apps like vehicle trafficking, fleet management, dynamic vehicle routing, and even locating hotspots. Imagine you are on vacation and using a navigation app to locate a restaurant. The navigation app uses a vector database to store the GPS locations of places to eat and visit. The app checks the database and provides a list of restaurants within a certain distance of your location. Vector databases provide distributed storage and parallel processing for horizontal scalability by distributing data and queries across multiple nodes or groups. This capability enables marketing and social sites to process big data and handle simultaneous queries for SEO calculations and user profile management. To reduce latency and boost overall speed, vector databases also use optimized caching and query execution plans. These capabilities speed the delivery of trending analytics to influencers and advertisers. Vector databases support auto-scaling and dynamic resource allocation to adjust to the ever-changing number of tasks. This capability enables your company to scale hardware and cloud resource usage for the best performance and lower costs. An example of a vector database used for marketing and social media is a site that maintains user profiles and keeps track of their hobbies, such as cycling, running, and swimming. As the number of users grow, the platform adds more hardware for the databases to handle the extra work of maintaining user profiles and tracking user interests, including clicks on products they like, without slowing down response times. In this video, you'll learn that organizations can make data-driven apps that work well and can be expanded to many areas using their strengths. You can use vector databases for image and video analysis, including feature aspects, similarity searches, and real-time data processing. Vector databases use embeddings and cross-domain suggestions to enhance the completeness of recommendation systems. GPS, fleet management, and real-time traffic routing suggestions are built on vector database geospatial processing capabilities. And vector databases enable marketing and social sites to scale resources to manage user profiles, deliver trend analysis, and optimize their cloud and other hardware use.
Welcome to this video, ChromaDB Key Concepts and Architecture. After watching this video, you'll be able to understand the core features and capabilities of ChromaDB, understand the different deployment options of ChromaDB, explain the architecture and workflow of ChromaDB, and understand data operations that can be performed by ChromaDB. ChromaDB is a vector database specifically designed to support various retrieval tasks. It offers the following capabilities: storage of embeddings and their metadata to efficiently store and manage vector representations of data. Vector search compares vector embeddings to find text based on semantic similarity using distance metrics such as cosine distance. Full text search to find relevant documents based on lexical or spelling similarity. Document storage to store entire documents, not just their embeddings. Metadata filtering can be used to narrow down search results based on metadata to improve the accuracy of the data retrieval process. And lastly, multimodal retrieval to retrieve and manage multimodal data, such as images, audio, and text, in a unified manner. ChromaDB can be deployed in one of two ways. ChromaDB typically operates using a client-server architecture, where the Chroma client connects to a Chroma server running in a separate process. The server can be launched either via the Chroma command line interface, including the core Chroma package, or by using a Docker image. The clients, whether local or remote, connect to the server using the HTTP protocol. For Python, Chroma can run in a standalone mode instead of the typical client-server setup. In standalone mode, both the server and client functionalities are run within a single process. This mode is useful for quickly testing Chroma's features or when the server is expected to always run on the same machine as the client. Let's take a brief look at Chroma's vector database architecture. The Chroma vector database architecture works in multiple phases. During the first phase, which is optional, you'll obtain embeddings. During this phase, you'll convert text, images, or data into their vector representations using an embedding model. This step is optional because you can offload the embedding step to ChromaDB if you want. In the next phase, you'll create collections. Similar to tables in a relational database, ChromaDB uses collections to store all of its data. The next phase is where you store data within the collections. If you created embeddings outside of ChromaDB, you would have to pass the embeddings to ChromaDB at this step. Otherwise, if you allow ChromaDB to handle embedding, then ChromaDB will calculate and store the embeddings from the documents in the background. Next comes the phase where you perform collection operations. ChromaDB lets you perform various database operations, including deleting, updating, or renaming your collections, giving you more options for organizing your data. In the final phase, you query and group data for the most useful information. ChromaDB lets users use text or vector queries to find information in groups based on semantic meaning or textual similarity. Moreover, ChromaDB allows users to filter documents on their metadata and document contents. ChromaDB supports multiple clients and integrations. The officially supported clients for ChromaDB are Python and JavaScript, and these are maintained by the Chroma core team. There are also several unofficial community-supported clients for ChromaDB, including Ruby, Java, Go, C#, Rust, and PHP. For more information on these clients and their supported features, visit the Chroma Ecosystem Clients page in the Chroma Cookbook at the URL displayed here. ChromaDB can also be integrated with popular frameworks and tools such as LangChain, LlamaIndex, and Ollama. And it provides native integration with embedding models from Hugging Face, Google, and OpenAI. Let's take a high-level look at an example of a typical ChromaDB workflow. The first step is to create a collection, which involves giving it a logical name. The next step is to add chunks of text and associated metadata to the collection. When you do this, ChromaDB automatically stores the text and handles the embedding process. Alternatively, if you pre-computed the embeddings before this step, you would supply those embeddings here along with the text. Lastly, you query the collection, and ChromaDB returns a list of the most similar results. Again, ChromaDB handles the embedding of your query automatically, so you don't need to embed the query text before running your query. By default, Chroma uses Euclidean distance to identify the most similar chunks within a collection. It also supports cosine distance and dot product calculation. Let's take a quick look at the performance features of ChromaDB. ChromaDB offers efficient similarity search capabilities as it is optimized for approximate nearest neighbor search, allowing users to find similar vectors quickly. Internally, Chroma uses an advanced algorithm called the Hierarchical Navigable Small World, or HNSW for short, for efficiently finding the approximate nearest neighbor according to the chosen distance metric. ChromaDB also offers good coding practices. The core of ChromaDB was written in Rust, which allows for 3 to 5 times speed improvements in querying and writing operations when compared to a core written in Python. Some of the most common use cases and applications for ChromaDB include the following: building personalized recommender systems based on user preferences, implementing efficient document search engines using vector or full-text search capabilities, retrieving images based on text queries using multimodal retrieval, and providing chatbots with semantic search and retrieval capabilities for context augmentation. In this video, you learned that ChromaDB is a powerful vector database designed for various retrieval tasks. ChromaDB supports multimodal retrieval, metadata filtering, vector search, and full-text search. Deploying ChromaDB can be done using client-server architecture or standalone mode. ChromaDB integrates with popular frameworks and supports multiple programming languages. ChromaDB uses an advanced algorithm for approximate nearest neighbor search, which efficiently finds the approximately closest chunks to a query within a collection. And ChromaDB is suitable for a wide range of applications, including recommender systems, document search, image retrieval, and AI-based chatbots. Welcome to this video, Essential Database Operations in ChromaDB. After watching this video, you will be able to create collections in ChromaDB, modify collections in ChromaDB, add, update, and delete documents from collections in ChromaDB. In this video, you will learn how to create and modify collections, as well as how to add, update, and delete documents. These operations form the foundation for building intelligent, vector-based applications that leverage ChromaDB's powerful capabilities. First, let's look at how to create collections in ChromaDB. Collections are a way to organize your data. To get started, you import ChromaDB and embedding underscore functions, which allow you to define an embedding model. Then you define the embedding model. In this case, we are using a model from sentence transformers, and we define it using the sentence transformer embedding function. Then you define your ChromaDB client and use the client's create underscore collection method to create a collection. Here, we're creating a collection named my underscore collection with a description in its metadata. Metadata can help you keep track of the purpose and contents of your collection. The last line generates the output, which in this case is just the collection name we specified earlier. If you already have a collection you would like to connect to, you can establish a connection to it using the get underscore collection method. In this particular case, we are connecting to the my_collection collection, the collection we defined before. We can verify this by printing the collection's metadata, which in this case is the description we defined for my_collection. You can alter a collection by using the modify method. In this particular case, we are changing the name and metadata of our existing collection. Note that collection metadata in ChromaDB can accept any key-value pair that is useful for describing your collection. In this case, for demonstration purposes, we simply used the key, and assigned it to the value. And again, the last line generates the output, which in this case is the modified metadata, which simply consists of our key-value pair. Please note that certain changes, such as modifying the embedding model or distance metric, cannot be made with an existing collection. To apply these changes, you need to clone the collection, which can be an expensive operation computationally if you have a substantial amount of data stored in your collection. Adding data to your collection is simple. Use the add method to insert documents using a list. You can also provide optional metadata by passing a list of dictionaries to the metadatas parameter. There are no limitations on the contents of the metadata. In this case, we are passing the document's source and version information. Make sure to include an ID for each document in a list passed to the ID's parameter. You can get data such as documents from a collection using the get method. Note that the get method returns a Python dictionary. When you run the collection.get method, the output returns all the documents in the collection. Note that the output does not return the embeddings. However, the embeddings are actually stored in the collection, but they are not displayed by default to keep the output clean. To see the embeddings, we need to pass include equals embeddings to the get method. Moreover, in addition to pulling out all the documents in a collection, you can retrieve individual documents by passing their IDs to the get method. To update existing data in your collection, use the update method. This enables you to modify one or more records based on their IDs. In this code example, we are updating the document about LangChain by specifying its ID, ID1. And we are changing both the metadata information and the text of the document. Note that ChromaDB handles re-embedding in the background, recomputing the embeddings for the document as soon as the update is submitted. Finally, you can either pass in a list of IDs to delete, or use the where filter to filter on the document's metadata. Note that you can also use a combination of IDs and filters. In this example, only the document pertaining to llama index will be deleted because that is the only document for which the where statement resolves to true. ChromaDB uses an algorithm called Hierarchical Navigable Small World, or HNSW, to perform approximate nearest neighbor searches. The space parameter in HNSW defines the distance function used in the embedding space. By default, this is set to L2, which stands for the squared L2 norm. Other supported options include cosine for cosine distance and IP for the inner product or dot product distance. To specify the distance function, pass your chosen value to the space key when configuring a ChromaDB collection at creation time. In this code example, when we create a collection called my_collection in the configuration dictionary, we pass cosine as the value of the space key when configuring HNSW. In this video, you learned that ChromaDB operations form the foundation for building intelligent, vector-based applications. Collections are a way to organize your data within ChromaDB. You define your embedding model using ChromaDB's embedding functions. You create a collection using the create_collection method. Metadata helps you keep track of the purpose and contents of your collection. You connect to an existing collection by using the get_collection method. You alter an existing collection by using the modify method. You use the add method to insert documents into a collection. You get data from a collection using the get method. You update existing data in a collection by using the update method. You delete data from a collection using the delete method. And you use the HNSW space configuration parameter to specify the distance function when performing approximate nearest neighbor searches in ChromaDB. Welcome to this video, How Vector Databases Power RAG. After watching this video, you'll be able to describe what RAG is and the problem it solves, describe each of the key steps in a RAG pipeline, explain why you should use vector databases to perform many of the steps in a RAG pipeline, and describe the pitfalls to avoid in a RAG pipeline. In this video, we'll explore how vector databases are not just a part of Retrieval-Augmented Generation or RAG, they're the backbone of it. So let's walk through how vector databases power the RAG pipeline. But first, let's recap what RAG is. RAG is a framework that enhances language models by retrieving relevant information from external sources and using it to generate more accurate, grounded responses, and thereby reducing the amount of potential hallucinations that may occur. LLMs, while capable of processing large amounts of data, have limited context windows, so it's not possible to include all information in a single prompt. Moreover, their knowledge is frozen at the point at which they are trained, and they can hallucinate facts. RAG addresses these issues by retrieving and injecting relevant knowledge into the prompt. Let's have a look at an example of all the steps in a full RAG pipeline. First, source documents that are relevant to the use case are provided and potentially split into smaller chunks. Next, the source documents or their chunks are embedded. Then, these sources and their embeddings are stored in a vector database such as ChromaDB. Next, a user's prompt is received. Then, this user's prompt is embedded. A retriever then selects the chunks from the vector store that best match the user's prompt. Next, the retrieved text is combined with the user's original prompt to produce an augmented prompt. And lastly, this augmented prompt is passed to the LLM to produce a context-aware response. Vector databases play a central role in the RAG pipeline. They can handle several key responsibilities such as embedding both source documents and user prompts, storing those embeddings, retrieving the most relevant matches, and supplying the retrieved content for prompt augmentation. This represents the full extent of what most modern vector databases are capable of. However, some of these steps, such as embedding the documents and prompts, steps 2 and 5, can also be performed externally. In such cases, the vector database is used primarily for storing and retrieving vectors. Let's now discuss why you would want to use a vector database to perform most steps inside a RAG pipeline. First off, using a vector database helps prevent critical mistakes, such as accidentally using different embedding models for source documents and user prompts, or incorrectly linking embeddings to their corresponding source documents. Secondly, development becomes faster and cleaner when more steps are offloaded to vector databases. With fewer moving parts and less custom logic, your codebase stays simpler and easier to maintain, which in turn makes it faster to implement and debug. And lastly, performance is a major advantage. Vector databases are built for high-speed, scalable semantic searches using advanced indexing algorithms. Custom-built alternatives typically cannot match this performance without significant optimization effort. Vector databases are powerful, but even with the right tools, there are common mistakes to watch out for in a RAG pipeline. Some of these pitfalls can be avoided by using a vector database. Others require more careful attention. For example, using different embedding models for your documents and queries can break retrieval entirely. So use the same embedding model throughout. Vector databases usually handle this automatically. Another pitfall is choosing a poor chunking strategy, creating chunks that are either too large or too small, which can also negatively affect performance. Therefore, choose a chunk size that is long enough to preserve meaning without including too much irrelevant content. Another common pitfall is forgetting to re-embed your content after changing the data, distance metric, or embedding model. For some databases, such as ChromaDB, this cannot be done on an existing database and might necessitate cloning your collection. And finally, just because something is retrieved doesn't mean it's the best answer. Therefore, you should always test your results, because a little tuning can make a big difference. Vector databases are essential to RAG, but they don't do everything. Some RAG pipeline tasks usually happen outside the database. For example, chunking is usually done before data enters the vector database. Advanced retrieval logic, such as filtering and re-ranking, may require extra tools. Prompt augmentation is also typically handled outside the database. And integration with LLMs is not built into most vector databases. That's where RAG frameworks fill the gaps by connecting all the pieces. Tools such as LangChain and Llama Index wrap around your vector database and help manage the pipeline from document prep to final response. These frameworks provide additional structure and simplify the development and deployment of your RAG application even further. In this video, you learned that RAG enhances LLM response quality by retrieving relevant external information, helping the model generate more accurate and well-supported outputs. Vector databases are the foundation that makes retrieval-augmented generation work. The tasks vector databases can perform in a RAG pipeline include embedding source documents and user prompts, storing embeddings, retrieving most relevant matches, and providing the retrieved content for prompt augmentation. Using a vector database for all relevant RAG steps helps prevent critical mistakes, speeds up application development, and optimizes performance. Some RAG pipelines, such as chunking, advanced retrieval logic, prompt augmentation, and LLM integration, usually happen outside the database. And RAG frameworks such as LangChain and Llama Index can wrap around your vector database and help manage the full RAG pipeline, simplifying RAG application development even further. Congratulations! You've reached the end of this course. Let's take a moment to reflect on your journey, where you gained some essential knowledge on vector databases, similarity search, and ChromaDB that will help you contribute effectively to the development of Retrieval-Augmented Generation, or RAG applications. Let's review some key aspects of what you learned throughout the course. Vector databases simplify data storage, organization, and retrieval by organizing data points in a multidimensional space based on their proximity. Vector databases can handle complex data types and the analysis of non-traditional data, including relationship data such as social likes, geospatial data, and genomic data. These types of data are difficult for traditional systems to store and manage. When using traditional databases, these data types often need a lot of pre-processing and transformation. A traditional relational database stores information in the form of tables, whereas a vector database stores data as high-dimensional vector data, also referred to as vectors. Vectors are mathematical objects that are defined by their size and direction. Vectors can represent many kinds of data, including images, sounds, text files, pattern data, map data, genomic information, and others. Vector-based database types include in-memory, disk-based, distributed, graph-based, and time-based databases. You can use vector databases for image and video analysis, including feature aspects, similarity searches, and real-time data processing. Vector databases can also be used to enhance recommendation systems. GPS, fleet management, and real-time traffic routing suggestions are built on vector database geospatial processing capabilities. Vector databases enable marketing and social sites to scale resources to manage user profiles, deliver trend analysis, and optimize their cloud and hardware use. Similarity search is the process of finding items in a dataset that are most similar to a given query item. It is widely used in recommendation systems, image and video retrieval, natural language processing, and biometrics such as facial recognition. At the core of similarity search is a distance or similarity metric that quantifies how alike two data points are. ChromaDB is a powerful vector database designed for various retrieval tasks, and it supports multimodal retrieval, metadata filtering, vector search, and full-text search. You can deploy ChromaDB in client-server mode or standalone mode. You can use metadata filtering or document filtering for queries in ChromaDB. ChromaDB uses the HNSW advanced algorithm for approximate nearest neighbor search, which efficiently finds the approximately closest chunks to a query within a collection. ChromaDB is suitable for a wide range of applications, including recommender systems, document search, image retrieval, and AI-based chatbots. ChromaDB operations form the foundation for building intelligent, vector-based applications. Collections are a way to organize your data within ChromaDB. You use a variety of different methods to create, modify, update, and delete collections in ChromaDB. Metadata helps you keep track of the purpose and contents of your collections. The HNSW space configuration parameter is used to specify the distance function when performing approximate nearest neighbor searches in ChromaDB. RAG enhances LLM response quality by retrieving relevant external information, helping the model generate more accurate and well-supported outputs. Vector databases are the foundation that makes Retrieval-Augmented Generation work. The tasks that vector databases can perform in a RAG pipeline include embedding source documents and user prompts, storing embeddings, retrieving the most relevant matches, and providing the retrieved content for prompt augmentation. Using a vector database for all relevant RAG steps helps prevent critical mistakes, speeds up application development, and optimizes performance. Now that you've reviewed some of the fundamental ideas presented in this course, remember each module's glossaries and cheat sheets. You can use these assets to quickly reference much of what you learned. If you are not already enrolled in our IBM RAG and Agentic AI Professional Certificate program, of which this course is a part, we encourage you to do so. Depending on your schedule and the number of courses in the program, this program will take about 1 to 2 months to complete. Each program contains multiple hands-on labs and a final project. The professional certificate programs also have a capstone course where you synthesize and showcase all of the skills you've learned throughout the program. Congratulations on completing this course, and thank you for being a part of this learning journey. As a next step, we recommend you continue your learning journey and keep applying your new skills. Here's wishing you all the best.